The cosmos stretching above us is studded with countless stars and planets, each possessing its own unique characteristics. Stars, these colossal celestial bodies, are capable of nuclear fusion, transforming hydrogen into helium within their scorching cores and releasing immense amounts of energy. This heat generates internal pressure that pushes outward, but the powerful force of gravity counteracts this expansion, maintaining a delicate equilibrium and ensuring the star's stability. Planets, unlike stars, cannot sustain nuclear fusion. Although their interiors are subjected to enormous pressure, they never reach the critical temperatures required to ignite nuclear reactions. Instead, a planet's gravitational compression is balanced by the pressure of its gaseous envelope. Jupiter serves as a prime example. Its mass is only about 1% of what would be needed to initiate hydrogen fusion. This clearly illustrates the fundamental distinction between even the largest planet and the smallest star. If Jupiter's mass were significantly greater, it would eventually become a star, as internal pressure would reach the threshold necessary to ignite hydrogen fusion. Yet between these two categories lies an intermediate class of objects. In the vastness of space, there exist celestial bodies larger than planets, but too small to become true stars. These unique entities occupy a special niche in astronomical classification. By the late 1950s, astronomers had begun to develop a deeper understanding of stellar physics. They started analyzing the equations governing hydrogen to helium fusion and applied them to existing observational data. In the 1960s, the concept of a minimum mass star emerged. Calculations showed that any object with less than 0.075 solar masses, equivalent to roughly 75 times the mass of Jupiter, could not compress and fuse hydrogen. Such an object might form from a collapsing cloud of gas and dust, just as the Sun did 4.6 billion years ago. But instead of igniting as a star, it would gradually cool. Though initially hot due to its formation, it would steadily radiate away its heat into space and ultimately become a cold, inert mass. Scientists faced a challenge in naming this new class of objects. The term black dwarf was unsuitable, as it already referred to a hypothetical end stage of white dwarf evolution. Some suggested substellar objects, but this label never gained widespread acceptance. While low-mass stars glow red, these new objects emit primarily in the infrared and are nearly invisible in optical light, placing them spectrally somewhere between red and black. Astronomer Jill Tarter, renowned for her work on the search for extraterrestrial intelligence, proposed the term brown dwarfs. Though these objects aren't actually brown, the name stuck. Research into brown dwarfs continued actively, yielding theoretical insights, but no confirmed detections. As noted, astronomers classify stars by temperature. The hottest are designated O, followed by B, A, F, G, K, and finally the coolest, M. However, in 1988, scientists discovered a star even cooler than Class M. This object became the prototype of a new spectral class, labeled L, chosen simply because the letter hadn't been used before. Subsequent discoveries revealed more L-type objects, but these were still true stars, capable of hydrogen fusion, not brown dwarfs. Young brown dwarfs are very hot and visually resemble L-type stars, making them difficult to distinguish. But a key diagnostic emerged. Low-mass brown dwarfs contain lithium, whereas stars do not. Lithium, the third element in the periodic table, can also undergo fusion,
but stars burn through it rapidly in their youth.
Brown dwarfs with masses below about 65 Jupiter masses never reach temperatures high enough to fuse lithium. Thus, detecting lithium through detailed spectroscopy became a reliable method for identifying brown dwarfs and differentiating them from stars. Though imperfect, this technique proved effective. In 1995, while studying the Pleiades star cluster, a group easily visible to the naked eye, astronomers searched for its faintest members to complete its stellar census. Their deep understanding of the cluster allowed them to identify very low-mass, dim stars. During this survey, they found an anomalous object dubbed Tade 1, red, cool, and rich in lithium. Stellar models indicated its mass was about 50 times that of Jupiter, or 0.05 solar masses, confirming its substellar nature. This marked the discovery of the first confirmed brown dwarf. Soon afterward, a faint companion was found orbiting the star Gliese 229. Spectral analysis revealed something even more unusual. It contained lithium, confirming it as a brown dwarf, but also showed strong methane absorption. Methane, a volatile compound, breaks down at even moderate temperatures, indicating that Gliese 229b was significantly cooler than Tade 1. This led to the creation of a new spectral class, T-dwarfs. In 1997, Gliese 229b became a target for the Hubble Space Telescope. Its spectrum was studied in detail. No visible light was detected, but it shone brightly in the infrared. Nothing like it had ever been observed before. The discovery of this object, just 2 years after the first brown dwarf, sparked intense, long-term research into low-mass stars and brown dwarfs. Many more brown dwarfs were soon found. In 2009, NASA launched the Wide Field Infrared Survey Explorer, WISE, a space telescope designed to detect infrared emissions. WISE has since uncovered hundreds of brown dwarfs, with the count still rising. A new spectral class, Yai dwarfs, was added to the sequence, joining O, B, A, F, G, K, M, L, and T. Despite their name, brown dwarfs aren't necessarily so cool they emit virtually no visible light, appearing utterly black to the human eye. Others glow faintly with a violet hue. Initially, scientists expected them to appear red due to their low temperatures, but reality proved more complex. Molecules in their atmospheres selectively absorb certain wavelengths of light. Methane, water vapor, and other compounds absorb specific colors, sometimes red light more strongly than blue, shifting their apparent color toward violet. Since brown dwarfs emit mostly in the infrared, beyond human vision, astronomers use false color imaging to visualize them. In these representations, short infrared wavelengths are colored blue, medium wavelengths green, and long wavelengths red. Because brown dwarfs peak in medium infrared, they often appear green in such images, standing out clearly even among thousands of stars. One of the most counterintuitive traits of brown dwarfs is that increasing their mass doesn't come in stark contrast to everyday intuition. While combining two lumps of clay makes a bigger lump, and the same holds for planets and stars, brown dwarfs behave differently. Adding mass increases their internal density and alters their internal structure, but not their size. A brown dwarf twice as massive as Jupiter is roughly the same size, or even slightly smaller. Thus, the boundary between a massive planet and a small brown dwarf is blurry. Nature doesn't draw sharp lines between categories. Some scientists argue that planets form within protoplanetary disks around stars, while brown dwarfs form directly from collapsing gas clouds, like stars. Consequently, two objects with identical mass and appearance could be classified differently based solely on their origin. This concept remains debated among astronomers. For instance, brown dwarfs above 65 Jupiter masses confuse lithium, and those above 13 Jupiter masses confuse deuterium, a heavy isotope of hydrogen with one proton and one neutron. Yet neither fuses ordinary hydrogen, so neither qualifies as a true star. Delving deeper into these thresholds is arguably arbitrary. The author suggests it's more meaningful to view brown dwarfs as hybrid objects, sharing properties of both stars and planets. Their atmospheres behave in extreme ways. In hotter ones, iron vaporizes. In cooler ones, it condenses and rains down as molten metal. The closest star to the Sun is Proxima Centauri, a red dwarf orbiting the Alpha Centauri binary system at 4.2 light-years away. But in 2013, astronomers discovered Lumen 16, a pair of brown dwarfs just 6.5 light-years from Earth, making them the third closest known stellar system. This raises the possibility that an even cooler, closer brown dwarf might exist. It can't be in our solar system or the Oort cloud. If it were, we'd have seen it. But it could lurk just a few light-years away. While it's unlikely we'll find a true star closer than Proxima Centauri, the existence of brown dwarfs was once considered equally improbable. This suggests our astronomy textbooks may soon need rewriting. Today you learned that brown dwarfs occupy a middle ground between giant planets and small stars, and that large numbers of them have only recently been discovered. Despite their substantial mass, the most massive brown dwarfs still cannot fuse hydrogen, distinguishing them from true stars. This program was produced in collaboration with PBS Digital Studios. Visit their channel for more episodes. This episode was written by Phil Plait, edited by Blake DiPastino, with scientific consultation by Dr. Michelle Thaler. Directed by Nicholas Jenkins. Edited by Nicole Sweeney. Sound design by Michael Aranda. And graphics by Thought Cafe.